The next step in understanding star magnitudes is being able to do the math to calculate them, both for apparent magnitude lowercase m and for absolute magnitude uppercase M. As far as doing the math goes, there's generally two kinds of astronomy student, ones who like math and ones who kind of don't, or don't really care much either way. What I'm going to do here is show you how to solve these kind of problems in two different ways. One that's fairly straightforward but is kind of heavy on the math, and another way that's kind of longer but doesn't require you to do as much complicated math. The key, as discussed in the very first one of these videos, is that by definition, two stars that are 5 magnitudes apart, let's say a 1 and a 6, are different by a factor of 100 in terms of their true brightness. If you take a factor of 100 times and divide it into 5 equal increments, then you get that factor of 2.5 that was mentioned before. It's closer to 2.512. So let's suppose you've got star 1 that has some brightness B1 and magnitude lowercase m1, and some other star, star 2, brightness B2, magnitude m2, and you want to compare how much brighter one is than the other. So this is how you do it. The difference in their two brightnesses, expressed as a ratio, is 2.512 to the difference in their magnitudes. The only thing to point out here is that we have to switch the order M2 and M1 here because bright equals a small magnitude, so that keeps these ratios consistent with each other. And for absolute magnitude lowercase m, then the relative value of their luminosities is given by a similar formula, except this time you have absolute magnitude in the power. I'm going to give a couple of examples here, and for these examples, I'm going to choose stars that are listed in the chart that I gave you that's inside the document that's called Magnitude Note Page and Practice Problems. So you can look up these numbers inside that note page. In this example, Deneb's apparent magnitude is 1.25, whereas Barnard's star, a very, very dim star that was hard to discover, was about 9.54. When you plug those two numbers into the formula, you get 9.54 minus 1.25 up here in the exponent, which is about 8.29, and 2.512 to the power of 8.29 is about 2070. So the answer is that Deneb is about 2100 times brighter than Barnard's star. In this second example, I'm using luminosity instead of brightness, so we're talking here about absolute magnitude rather than relative magnitude. So when you look up the absolute magnitudes of the Sun and of Sirius A, here's what they are. Plug this into the formula, and you get a value of about 23. So Sirius A is 23 times more luminous than our Sun. The only reason that it is dim compared to the Sun is because it's a lot farther away, several light years. On the other hand, Sirius A is inherently a more luminous star than the Sun, and the main reasons for that are that it's a little bit hotter and it's a little bit bigger.